Yes. Paravi,
Yes, sir.
thank you for joining. And you saw already in group we sent two images. Did you see?
Yes, sir.
So you should take those notes. Huh?
Yes, sir. I saw.
Yeah, yeah. You should take that notes.
Sir,
Huh?
our timing, new timing.
Yeah.
Sir, our new timing.
You keep some space. Then later you take these notes. Okay. Okay. Now resistors in parallel. You see the diagram, right? Resistors connected in parallel. Hello.
Yes, sir.
So parallel means they all are connected. Their ends, you see, resistor R1 and resistor R2, R3, R4. Their ends are connected together. Okay, the upper ends of them in common, lower ends in common. That is called parallel. So they are connected in the same end, all of them, right? Both the ends are connected together. Now calculation. For parallel combination, resistance can be calculated using this formula. Rp is the total resistance of the circuit. So 1 by Rp equals 1 by R1 plus 1 by R2 plus 1 by R3. This will write the formula. For example, if we have three resistors, 2, 4, 8 ohms connected in parallel, then their combined resistance will be 1 by R2, 1 by 2 plus 1 by 4, 1 by 8. If you calculate, it comes 1 by Rp equals 0.875. Then you have to reverse it. Note that we must invert this to find the total resistance Rp. So Rp equals, if you reverse it, it comes 1.14 ohms. And at last, the relationship results in a total resistance Rp that is less than the smallest of the individual resistors. That means we have 248 these resistance, and the combined resistance will be always lower than even the smallest resistance. It's only 1.14. Is it clear, everyone? Hello? Parallel
Yes, sir.
resistance connection is clear, and the calculations. So you draw it, huh? Resistors in parallel, you draw it, then you write the formula.
Sir, done with the diagram.
Yes, done.
Yes, sir.
Any questions here, anyone?
No, sir.
The formula and the numericals are also done, right?
Yes, sir.
Okay. They who are not done yet, you can go with the group. The image sent to group. Now we are going with a new term, new quantity, that is resistivity. Before before going to resistivity, we are having some discussions. Then you'll understand it more. You write the heading resistivity. Huh? Now, for example, Farabi is driving a car. Farabi, hello Farabi.
Yes, sir.
You can drive a car, right?
No, sir.
No, not yet. Okay, inshallah you can do it. So, for example, you are riding on a bicycle. Is it possible?
Sir, it is possible.
Farabi, do you know how to ride a bicycle?
Yes, sir.
Okay, very good. So, for example, you are going from your house to school with that bicycle. Okay, this is one track that you are going from your house to your school. Okay, your house. Where is your house?
Adabod.
Where?
Adabod.
Katabon or Adabor?
Adabod.
Okay, Adabor,
Adabod, sir.
Adabor, Adabor. Okay, lots of others are there, right? Gingers. Okay, so that one from Adabor to your school is not a big distance, small distance. But sometimes it happens due to COVID-19. You have lockdown, right? But you have to go to
Yes,
your
sir.
hometown. Where is your hometown?
Ready.
Feni. Okay. So if you want to go to Feni, you have nothing but your bicycle. That one is very long path, right? Isn't
Yes,
it?
sir.
So you will get tired, right? If you want to go Feni with your bicycle, you will get very tired, right?
Yes, sir.
Okay, so does electrons. If electrons they are going through a short wire or short conductor, then they can go easily, smoothly. But if the electrons they are going for a long path, long wire, long conductor, then they get tired. Okay, Everyone, you are understanding? Hello?
Yes, sir.
So when the electrons they are going through a longer wire, their flow becomes slower, right? And they get tired, they have resistance, more resistance, right? Can we say they are facing more resistance? Hello?
Yes, sir.
So we write here this idea first, that if uh, the conductor is longer than resistance increases. That means resistance and length of the conductor is directly proportional, we can say, right? That means R is directly proportional to longer wire, right? Length of the wire. Have you understood, everyone, this matter? Hello?
Yes, sir.
Is there
Yes,
anyone
sir.
who did not understand? Mahi Khan, Monica, Mariam, Maimona,
No, sir, understood.
you have understood?
Yes, sir.
No means yes, right? Mahi, your no means yes, you understood, right?
Yes, sir.
Yes, you understood. Okay, so your no means you don't have any question, right? Mahi, hello Mahi.
Hello,
Your
sir.
your no means you don't have any question, right?
Yes, sir.
Yeah, okay. So now it's your turn, Mahi.
Yes, sir.
You can drive a car.
No, sir.
What you can drive?
Sir,
Sports
I
car.
can.
Sports car in the games, right?
Yes, sir.
Okay. So for example, you have a game, and over there you have one sports car. You have two roads. Okay. How many?
Two,
Two.
sir.
Okay. So first one is very narrow, and second one is very wide. Okay, have you
Okay.
understood?
Yes, sir.
One of the roads narrow, another one is wide. So
Yes, sir.
where your car will be easier to drive faster, narrow one or wide one?
Sir, the wider one.
Wider one, yes, yes. So does for electrons. So does for electrons. If
Electrons.
the electrons they are getting wider path, thicker wire, thicker wire, fat wire. Have you understood?
Yes, sir.
Fat Some people are very fat, right? So this time
Yes, sir.
fat has some advantages. If the wire is fat or thicker, then the electrons can move easily. We can say the current can flow easily, right?
Yes, sir.
And we can say other way around, if the wire is thicker, then resistance will be less. Can we say that? Hello?
Sir, no.
Again, I'm repeating, if the wire is thicker, the current is more, right?
Yes, sir.
So the
Yes, sir.
resistance will be less, isn't it?
Yes, sir.
Yes, sir.
Because current and resistance, they are opposite to each other, isn't it?
Yes,
Yes,
sir.
sir.
So if the current is more, that means resistance will be less if the wire is thicker, isn't it?
Yes, sir.
So resistance and the thickness of the wire, they are inversely proportional. Thickness of the wire is also called cross-sectional area. What does it call? Hello?
Cross-sectional area.
Cross-sectional area.
Cross-sectional area, because you have the wire, most of them, they are cylindrical shape, right? Isn't it?
Yes, sir.
And if you have the slice of the cylindrical shape things, then it becomes like a small circle, right? Isn't it?
Yes, sir.
So cross-sectional area means pi r square over here. If you know the diameter of the wire, that means you will get the cross-sectional area. If the diameter is more, the cross-sectional area is more. If the radius is more, the cross-sectional area is more. Is it clear?
Yes, sir.
So if the cross-sectional area is more, if the diameter is more, if the radius is more, that means your resistance will be less. Inversely proportional, right?
Yes, sir. Inverse.
Yeah. So we write it now here. If the wire is, if the conductor, if the conductor is thicker. Thicker means diameter,
Sir,
Fat.
more fatter.
diameter is greater, right? Thicker means diameter is greater, or cross-sectional area is greater, right? We write more easier, like diameter, then slash radius, then slash cross-sectional area. Greater. Okay, that's it. If the conductor is thicker, diameter or radius or cross-sectional area is greater, then resistance is less. That means we can write R. R is standing for resistance, and cross-sectional area is A, capital A. So we can write 1 by A. inversely proportional. I am giving the proportional symbol as well. So here you have any questions? Anyone?
No, sir.
One, two, three, four, five. Image five. So have you written this?
Yes, sir.
The relationship of resistance, length, cross-sectional area.
Yes, sir.
Very good. Now, yes. So we have two equations here, or two relationship here. One is R is directly proportional to L. Another one is R is inversely proportional to A, cross-sectional area. Now, if you combine this both, you continue, huh? If we combine both the relation above, then we get what we get R L by A. Can you write this way? Hello.
Yes, sir.
Now, afterwards, we write this way: R equals rho L by A. Here, rho is the proportionality constant. Constant which depends on. Here row, I kept some space to write row. I will write it after finishing the text writing, then I will draw it. That's why I kept it space. You can write, you know already what the symbol of row. Here rho is the proportionality constant which uh, depends okay, which depends later which is known as property, oh, which is known as resistivity. Resistivity of a conductor. For a certain element, like we have copper. For copper, resistivity is constant. For a certain element, for example, copper, where copper where the resistivity 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 is fixed or is a constant. The SI unit of resistivity unit is of resistivity is ohm meter. Ohm meter. Okay. Then I draw the symbol of ohm here. This is a Greek letter rho, which is used to symbolize or represent resistivity. One, two, three, four, five, six. Yeah, six. So, any questions here? Anyone? Hello?
No,
Hello?
sir.
Farabi? Farabi,
Yes, sir.
have you understood the discussion?
Yes, sir.
Any questions? Do you have any questions, Farabi?
No, sir.
Okay. So if you don't have question, then read this. I'm opening. Yeah, read from here. Farabi, resistivity, you read this.
Resistivity.
Hmm.
Every resistivity is a fundamental property of a material that quantifies how strongly it resists electric current. As low resistivity indicates a material that readily allows electric current, resistivity is commonly represented by the Greek letter rho. Its SI unit is ohm meter. Ohm meter. Recall the SI unit of resistance is ohm. So there is a little difference between resistance and resistivity. Resistivity is a constant for a thickness of the conducting material, even if it is the same element. To calculate the resistance R of a wire, we need to know three things. Its length L, the longer the wire, the greater its resistance. Its cross-sectional area, greater the area, the resistivity of the material R is the greater the resistivity, the greater its resistance. Resistance plus resistivity into length by area.
Yeah. Then read the equation R equals rho L by A.
Well, to L by A, the equation defines resistivity. We can rearrange it to get a formula for resistivity. Resistivity is equal to resistance into area by length.
So we are done with resistivity, right? Now light dependent resistor. Yeah. Adrita. Adrita.
Yes, sir. Yes, sir.
Yeah. So read light dependent resistor.
Light dependent resistor LDR. An LDR or light dependent resistor is also known as photoresistor, photocell, photoconductor. It is one type of resistor whose resistance varies depending on the amount of light falling on its surface. When the light falls on the resistor, then the resistance decreases.
Okay, so here you write the heading light dependent resistor, then only write this part. Okay, when the light falls on the resistor, then the resistance decreases. If resistance decreases, then what will happen to current? Hello, hello.
Yes, sir.
if the resistance decreases, what will happen to the current?
And the current will increase.
Yeah, current will increase. So remember it, huh? Light dependent resistor we are using in street lamps, we are using in intruder alarms. We will get the applications later. Just I'm informing you now. And you write only this light dependent resistor. When the light falls on it, then the resistance decreases. So we are done with uh, topic 19 completely by this discussion. Next we have DC circuits. After the earlier discussions, you see we are having circuit symbols of different components or appliances. So from there DC circuit starts. Okay,
Okay, sir.
1 2 3 4 5 6 7. Yeah, 7 images today. So that's all for today, huh? Everyone. Allah Hafiz, huh?
Thank you,
Allah
sir.
Hafiz, sir.
Assalamu alaikum.
Yes, sir.